Uh, so good afternoon, everyone. Welcome to my presentation on towards trustworthy outsourced deep neural networks. My name is Bok Dong, and this paper is in collaboration with Dua Ahmed, Bharat Samsatullah. All of us come from Montclair State University, and also we collaborate with Ryan Wang and Bill Lee, or from Jump City. So nowadays, deep neural networks are getting more and more popular because of their superior performance. And we see a wide application of them in face recognition and autonomous driving. Even though they bring a lot of performance boosts, still we see some problems raised by deep neural networks. One of the issue is that they require expensive computational hardwares, such as multiple powerful GPUs, and also to deploy a deep neural network, it requires extensive skills such as Docker, Kubernetes, TensorFlow, and usually small and medium-sized companies and organizations lack these skills and resources. So nowadays we see more and more companies and organizations are outsourcing their deep neural network models to a cloud-based service provider such as Amazon AWS and Databricks. In this outsourcing scenario, firstly, the data owner trains a deep neural network locally, and after that, it is deploys it to a server. And then authorized clients can send inputs to this server, which is going to provide the prediction results and send it back to either the data owner or the client. So it's true that this outsourcing strategy provides a cost-effective way to enjoy the benefits of deep neural networks. But at the same time, it raises several security concerns. One of the biggest concern is that the cloud-based server is usually untrusted, and it is possible for the server to return wrong prediction results. In practice, there are quite a few reasons for the server to do so. For example, the server may experience Byzantine failure, such as network connection error or software bugs. And also, a sloppy server may just return a random result, prediction results without running the prediction model in order to save computational cost. And in the worst case, a malicious server can launch adversarial attack and send specific prediction results to the data owner or the client, and which may lead to some which may lead to disasters in some cases. So, for example, think about one day when you're sitting in your auto-driving car and reading a newspaper. And usually the sensors and cameras installed on your car are collecting pictures and videos of the surrounding areas and sending these inputs to the cloud-based server to do object recognition or object detection so as to make the best decision. So if the server is malicious and say when your car sends such a traffic light image, and then the server just return a wrong result, which is saying, okay, this is a green light. And this wrong prediction result may lead to a tragedy. So we definitely want to avoid this. So in this paper, we focus on the integrity verification of outsourced deep neural network models. And specifically, we make the following contributions. So first, we propose a new attack named Scam, which allows the server to generate any wrong prediction result in a command and control fashion. And following that, to mitigate any adversarial attack, we design a verification scheme named Hero, which is based on homomorphic encryption. And also we conduct an extensive set of experiments on 2 benchmark data sets to validate our approach. So before I introduce our work, I want to firstly briefly mention homomorphic encryption. So a homomorphic encryption scheme is a set of 4 polynomial functions, which are key generation, encryption, evaluation, and decryption. And the power of homomorphic encryption scheme is that it supports the evaluation of polynomial functions in a ciphertext space. And so even though theoretically fully homomorphic encryption supports the evaluation of polynomial functions of any degree, in practice, we find that the evaluation overhead grows sharply with the increase of the degree in the evaluation function. So normally we want to limit the evaluation function to be low degree polynomials. And okay, so now I'm ready to introduce our attack based on steganography. So we give the name called scam. So a scam takes advantage of the least significant bit to hide the desired label or desired prediction result in the input. And and after the server receives this polluted input, the server will first decode the input and extract the desired prediction result, and it will just return the result without looking at the input sample. And so compared with existing adversarial attacks against outsourced deep neural networks, such as the data poisoning attack, backdoor attack, and target model poisoning attack, the scam is advantageous in the following ways. First, it does not require the access to training data. And in practice, this is usually infeasible because the training data is usually a private property of the data owner. And also, it does not need the adversary to collect separate poisoning data set. Also, it does not require model retraining in order to generate wrong prediction results for certain inputs. And most importantly, it guarantees 100% attack success rate compared with the other approaches, which may only have a success rate of or around 20%. This is a big advantage. So here, I showed we show two say the original image and the polluted image with the secret message label tree on the right hand side. So if the server receives the right image, it will just return tree as the label, and this may lead to a disaster when people are driving. So from these two examples, we can say that the polluted image is very similar to the original image. And to validate that, we calculate the LP-IPS score between any pair of original image and polluted image. So the LP-IPS score is a metric to evaluate the difference in terms of human beings. Okay, so the smaller is the value, a smaller LP-IPS value means the two input images are really similar. So among all our testing samples, we find that the LP-IPS score is always less than 1%, which means the attack is kind of like invisible. And so to defend against any adversarial attack on outsourced deep neural networks, in this paper we'll propose a verification mechanism based on homomorphic encryption. So the key idea is that after the server trains a neural network model, it will create a neural network by replacing the activation functions with low-degree polynomials. And also, we introduce a validator which will evaluate the neural network on the encrypted instances. So in this way, the validator does not need to access the testing sample so as to protect data privacy. So the validator can be another cloud-based service provider as long as it does not collude with the server. So this is the detailed framework of our verification scheme named Hero. I'm not going to introduce the details over here. If you are interested, please feel free to refer to our paper. So, and to validate our approaches, we did an extensive of experiments on two benchmark datasets, the MINISC and the SAFER10 dataset. So in this slide, we report the detection accuracy of Hero. So when we are using different approximation functions of the activation function. And here we can say that a higher degree usually leads to a better detection accuracy. However, a higher degree approximation function also means higher evaluation overhead. So, and we find that in general, as long as the degree is 2, you can reach a pretty good balance between the security and efficiency. And also here, we show the testing accuracy of the neural network. And so with regard to different number of training averages, and also we compare the testing accuracy of the neural network with the original network, which is displayed in the red line, and uses the ReLU activation function. So here we can say that again, as long as the degree reaches 2, the neural network has a pretty similar testing accuracy as to the original network. Okay, so and now I'm ready to conclude my presentation. In this paper, we focused on the security threats against outsourced deep neural models, and we are leading the efforts to build trustworthy services. And in the future, we plan to conduct more experiments to evaluate the verification overhead, and also we plan to use probabilistic verification approaches in order to further reduce the verification overhead. So, and thank you for your attention, and I'm more than happy to answer any question from you. Thank you.